among others. Next, please. The finite elements connected to each other by points, which are called joints. Due to the subdivision of the geometry, the mathematical equation governing the physical behavior will not be solved in an exact, but approximate way by this numerical method. The occurrence depends on the number of joints and elements. The general objective, next please, is analyze the structure composed by beams in the plane to interpret the behavior of the elements and its capacity to resist loads. We have three specific objectives. The first is develop a computer program that analyzes structures composed by beams in the plane to study the behavior of the elements produced by the distribution loads. And second, analyze one of the flat frames of the sheet steel structure to find out which element is the most critical using finite elements method. And the third, and finally, is to study two cases of boundary condition in the discretization to compare the physical behavior of the structural elements of the frame. The procedure. For the analysis of a frames of a ship, we start by discretizing the structure. We determine the number of elements and joints. Additionally, the position in which each joint is located. With the characteristic of each element, we calculate the area, inertia, neutral axis, angle, and others. In the structure, each element is composed of three parts. We have a tin pin, and on top of the tin pin is interdeck plate. Subsequently, we calculate the external forces to which each joint is subjected. As we can see, we have three types of elements. The first are those that are on the deck, and others is in the between deck. The second element are subjected to the side. And finally, the elements below the draft line are subjected to the hydrostatic pressure. The following equation were used for their calculation. Next, please. For the solution of the structural analysis problem using the finite elements method, we will use the numerical tools provided by Python. For the development of the computational program, we first need is to read the values that were previously calculated and which are shown below in this TXT file.
The second part of the program is solving global system. It transforms the information from the list to vectors and creates the matrix K by element. This matrix is added to the global matrix and then solving the linear equation system by the big value method to get the displacement and forces, and finally return the global matrix, global displacement and forces. For the third part is the analysis by elements, when the program creates two dictionaries, one for analysis as a bar and another as for analysis as a beam, and iterate in the range of the number of elements. Create the matrix T to get the local displacement and make two analyses. For the beam, create the vector of positions and calculate bending moment, shear force, stress, deflections, and the information is kept in the dictionary for the analysis as a beam. And another, for analysis as a bar, the calculation is the difference of the local displacements and stresses and loads. The information is kept in this dictionary. Then return the two dictionaries, and in the final process, create a file and print it, where the program opens the new text file, write the global matrix, global displacement, and the forces, iterate by element, and print two tables by elements, one for the beam analysis with the position, shear force, bending moment, stresses, and in another table with the strain, stress, load, and finally the program closes the text file and print it. So The the program was tested by solving a solved problem. In this case, two beam support on a ship deck. As you can see, the results are very similar to the real solution. For example, the global matrix that we have the same values, or the global displacement where they are the forces and display and global displacement are in the same order. It is the same for the beam analysis and bar analysis, as you can see.
So it's you, this slide.
And now for this data in the frame, we discretize the frame of the ship and get the data in the format to insert in the program.
Continue to my slide is the case 2.
Okay, the global displacement here, that we get the global displacement and the summary results, we can make that it makes sense because the displacement are no bigger than 6.67. That this case happens in the joint 11 and joint 5. It makes sense because these displacements are located in the parts that we don't have support. So we don't have any longitudinal reinforcements that avoid this displacement. And another analysis is the analysis by elements, that we have that the stresses are in the half. Makes sense because all stresses are no more than the yield point, and the bar analysis, the critical elements are 4 and 5. This is
4 and 5. Now in continuity with the process to analyze the case 2 of the second problem. In this problem, the boundary condition changed. Not only the joints 1, 8, and 9 are considered clamped, and the rest are only joints and any type of support, just joints. And with this, we obtain the following results. In the first place, the joints, next slide. In the first place, the joints with the greater displacement is the 2, because it doesn't have a longitudinal reinforcement that supports the load distributed in the element. Likewise, in this element is the most critical because it has the highest bending moment and their highest stress exciting the GL point, as you can see in the graph presented in the next slide. The blue curve is the one that expects the GL point, and the right side there is a bar diagram of the axial load per element, where by expansion we can notice that the most elements are in compression because it has no reinforcement and must support the other loads. Now, in the conclusion, sorry. In this slide, you can see the displacement of the joints in the case of joint 2 and 7 of the structural elements by applying the final element. Sorry, the 2 and 7 are the most notorious joints in the others. And for the conclusion, we developed a computer program that allows of use the physical behavior and structure arrangement by applying the final element method. And the other hand, the structure of the first case was analyzing was obtained the most critical element is element 3, because at the point is the 70% of the yield point and is considered safe. And for the recommendation in the next practice to select several discretion cases where the elements are increases or decreases to visualize the behavior in the structure. And thank you.
Okay, thank you. Right on time. Let me see the results. Two transparencies back. Yeah, there.
Here?
No, this one, yes. No, the figure, with the stresses. No, no. Similar to this, but in two transparencies ahead.
In case 2, the results are just
this one, yeah. I can see stresses. I guess it's newtons per millimeter square, right? Not stress newtons per millimeter, right?
Okay.
Right.
Yes.
Okay, that's one thing. The other, that's a minor thing. It's just a typo. My problem is that there is a curve, right, which reaches 600 newtons per millimeter square. What can you say about that?
It makes sense for us because here we don't consider the longitudinal structures, so the longitudinal reinforcement. So in this case, the structures will be don't have anything to avoid the displacement like the longitudinal reinforcement. And
Okay.
in our analysis, we corroborate the importance of the longitudinal structures. It is important that, as you could see, the stresses is above of the yield point, where is another case with in the first part that we consider the longitudinal and
Influence of them. Makes sense. Thank you. Miss Gutenberg.
Yes, Doctor.
Let's suppose that I want to specify the maximum deflection, permissible deflection in the structure, okay? How would you implement this calculation?
The next slide, your question said if my calculate.
No. Let's suppose for example, I design a structure, okay? So I'm going to analyze it using your program, but I'm worried not only about stresses, but also deflections. So let's suppose that I set up the maximum deflection that I can allow is 1 millimeter. How would you implement this maximum deflection in your code, in your program?
The maximum deflection.
Maximum allowable deflection.
Sorry, I don't understand the question. The maximum stresses.
No. Deflection.
Me salvaste la vida.
Okay, when we calculate the.
If you want to show me the code, in what part of the code would you consider that of your program, your code?
The part B, the flowchart, you can put this part.
Okay, go on, explain it to me.
Okay, when we calculate the global matrix and push the big value,
Mhm.
and this multiplied by the external force, the transpose of this matrix plus no, multiplied by the external force, we obtain the deflection. The displacement of H node joints. In this part,
Yeah, thanks.
thank you. Sorry.
No problem. Mr. Arias, where are you? Oh, here. Can you describe me the process in your code to store the results in an external text file?
Okay, and for that, let me see. Yes, this function, and in our program, we create a several definition to reduce the code lines. So in this case, we create the definition create a file. This definition would help the dictionaries created in the another steps.
Okay, that's enough. That's enough. That's enough. Thank you.
Okay.
Okay. Isaac, would you please let the next group?
Okay. Thank you, Doctor.
Okay.
Thank you.
That's all.
No problem. No problem. No problem.
Doctor, have a great day.
Okay. Good work. Good work. Mr. Barba, Ms. Freire, and Mr. Matute. Okay, you can share the screen so you can go on, please.
Okay,
What?
good morning.
Whenever you're ready, you let me know. Isaac, are we recording? Are we recording, Isaac?
Yes, doctor.
Okay.
Can
Okay,
you
go
see
on.
You are recording.
Yeah, I can. Yeah, I can
presentation?
see. Yeah, I can see the presentation.
Okay, I'm going to start.
Yeah.
Good morning. We are the group number 9, and we are going to present the analysis of a transversal frame of a ship section. This group is formed by Jose Barba, Ronnie Matute, and me, Thais Freire. Here, I'm presenting a table of contents, which have the introduction that it's going to be a short introduction of what is the finite element method and the main objectives of this assignment. And then we have the process, and we're going to have the flow chart, implementation of the program, and the discretization. On the point 3, we're going to have the results and the analysis and comparisons. And finally, we have some conclusions and recommendations. So at first part, in the introduction, we have what is the finite element method? Well, this is a numerical method using for solving engineering and mathematical physics problems. For example, in the case of extremely difficult geometry or material properties or some strange load, where the analytical solution it's not possible to be found, we can apply this finite element method, which consists in discretize the structure. It means that we partition the element or the domain to analyze each partition, and then we join them taking into account the continuity between these elements. It's important to mention that this is an approximation. This is not an exact solution, but it's a quite good one. Then, what is the objective of this one? It was asked to analyze the transversal section of a fishing vessel. This is the frame 101. As we can see, it has 2 distributed forces acting on 2 decks. It also will be considered the weight of the structural elements and the hydrostatic pressure acting under the draft line. So in the process, we implement the general flow chart that basically it starts input the information on the TXT, the required information to run the program, and then it follows the algorithm of the finite element method. As we can see, it says the big values, then we calculate the inverse, and also found the values of deflections, stresses, and deformations to finally create a TXT of the results that we obtain.
For the discretization, we divide the cross-section into 15 elements with 16 joints. The elements are mostly limited by the longitudinal reinforcements. However, in joint 5, it's defined by the draft that was the initial data of the problem. Also, in the producer curve of the sections, a greater numbers of the elements were implemented to model the discretization with a great similarity to the original sections. It's important to mention that the global reference is on the bottom of the center line sections. And the equivalent force of for the case for the death are showing in the 1, and equivalent force in pressures showed in the 2. Next. Next. Okay, in the text file, the text file follows the text structure. Large E is the number of the element, JI is the initial joint, JF, final joint, X and YI is the position of the first joint, and X and YF is the position of the final joint. A large A is the area, large E inertia, large Y is the joint modulus, and con is the boundary conditions in the first joint, S1X and Y, and M1C is the external force in initial joint, and second condition is the boundary condition is the final joint, and F2 X and Y and N2C is the external force in the final joint. Next.
Well, as you can see, a set of functions were created to run the program. The first function reads the data from the file and classifies. The second function that will create the right tab of each element. The third function created the global arrays. The fourth function located the big values depending of the boundary condition. Next. The fifth function will create the force matrix. The
list.
Function will create the list of properties. We will store a list with the formation, stress, and safety factor of each element. And the last function will locate the maximum and minimum stress. Each of the third function will be applied in the execution of the program to obtain the required data of each one of the elements. The advantage is that does not have limits with the number of the elements that can be analyzed as long as coordinates and boundary conditions are well defined. Next. Finally, the program will print and save in TXT file all the characteristics of each element, such as the element number, the length, the degrees, the formation, and the stress, and the safety factor. Yeah, observing that the safety factor of the FEM rated the 1, which indicates I will access the yield stress on the material. Next.
What are the units of deformation?
The deformation is not have units. Is
Is that the strain or displacement?
a strain.
Oh, okay. Sorry.
Yeah,
Go
I'm
on,
sorry
go on.
for this day.
No problem.
Yeah, next. In addition, the graphic reference is also shown, which says as a file PNG, where we indicate the location of each joints, the elements, their deformation, and located the maximum and minimum stress. And it's important to mention that the program is designed to analyze any type of the structure.
Mm-hmm.
Yes. And next.
Conclusions. The program is designed to analyze any transverse structure as long as has the enough information as a geometry data, external lobes, mechanical properties, so that input information with the structure and the TXT file. It was considered that the structure is safe because after analyzing each element, it was noticed that at any point, the maximum stress is bigger than the yield point of the steel. It was checked that the value of the stresses in the allowable range of the material. And recommendations to facilitate the development of the code, short exercise can be carried out with no results. For this way, to be sure that the length of the code are implemented, it will return correct values. Thank you.
Well, I'm going to present the program. I'm going to share.
Okay. You still have 1 more minute.
Okay. Well, this is the program. And I'm going to run. Yeah, for example, I'm going to find one. No. I'm sorry.
No problem.
Right, the one and insert there. Well,
Wow.
This is the presentation of the program. It's the joints and the maximum and minimum stress.
Okay.
And I look in the
Okay, that's enough. Miss Freire, can you hear me?
Yes, doctor.
Can you show me in the program the calculation of the bending moment distribution?
Can you put on the function? Well, we didn't calculate bending moment. We calculate the normal stress.
Okay.
So it is
no,
in
no. I don't want to see the results. I want to see in the program how you calculate it.
Can you put the function of the below below is no, up.
The program.
We define the function to.
Okay.
Yes,
define the function for what?
We didn't calculate. Yeah, we define the function first a function to find the maximum values of stresses. But when we implement in the main program, we did the process of the matrix. I mean, it was the first global matrix.
Yeah, but if you want to calculate the stresses in the case of bending, first you have to calculate the bending moment, right?
Mm,
Go on. After you
Yeah.
after you calculated the displacements, right? Solving the global stiffness matrix.
Yes.
Okay, and then what next?
Then put the main program that is below. Yeah, no, below. Down, yes. Here is the main
Okay.
the main program. So it calls the function that we define above. So it says the global matrix, it calls the matrix with the big values. Then we calculate the inverse as it says. It was also used a function to calculate the inverse. Then with that, we calculate the matrix of forces. I mean, it's a data given, but we put in the form of a vector.
Okay.
Then we it's here. Yeah. Then we create the matrix of that inner forces, and then here we show the matrix, the global matrix. After that, we obtain the deflections because we have already did all those process of the matrix of the inverse, and then we in the code. Well, then we found the values of the stresses and deformations.
But how did you calculate the stresses? That's my question. See, I can see that you get the inverse multiplied by the F force, and that gives you displacements.
Yeah.
Okay, go on.
Yeah, that's the line.
But the stress is give you the deflection, but that's the stress from the axial force. And what I'm interested in the deflection or the stress from the bending moment.
Oh, yeah. Sorry, doctor. The program
Doesn't not calculate that?
No. But I might implement this function, but I don't.
We didn't calculate that. Okay.
Sorry.
No problem, Mr. Matute. In your program, how can you identify the reactions, or how did you calculate the reactions in your or how can you calculate the reactions, Mr. Matute?
Okay, the reactions. Well,
Yes.
In the matrix force, identify the reactions, please.
How? Okay, how can you do it? How did you do it?
How can you do is the multiply the displacements for the inverse of K make on the global matrix.
Okay.
In this part, and in the TXT data, identify the external force for the multiplication. Yeah.
Yeah, but the thing is this, okay? The reactions are not data.
No, the data is the external force.
Yeah, okay. But where are the reactions? Did you calculate those, or how can you calculate them?
In the calculate.
Remember, when you have an instructor, okay?
Yeah.
You have an instructor. You have external forces from the wind, from the weight, and things from the pressure. The problem is that on the supports, okay, on the supports, those points cannot move, cannot rotate. And then you have a reaction from the foundation. And that reaction is the forces, external forces, which do not allow this point to move. So you have to calculate them after you solve for the displacements. These are not data.
No, the reaction is calculated for the multiplication, the displacement for the global matrix.
No, no. Yeah, but it's still there. You have to differentiate those points where you have supports, when you have geometric restrictions. Okay.
The boundary conditions, yeah.
Exactly, and the boundary conditions, yes.
The boundary conditions.
Here.
Yeah, but remember, the geometric boundary conditions, which do not allow to move or rotate, in those points, you have to calculate the reactions. Okay, people, I'm late. Okay, that's it. Thank you very much. Isaac, please let the next group in.
Thank you, Doctor.
Okay.
Hey, Doctor.
Good morning, Doctor.
Good morning. Are you ready? You can share the screen.
Morning.
Good morning,
Good morning.
Doctor. You can see the projection?
Yeah, I can see it. Go on.
Yeah. Good morning to everyone. We are the group number 3, and we are going to talk about the implementation of finite element method to obtain the deflections and internal forces of a floor frame of a ship. It is different analytical methods we can use to solve structural problems in which are involved the deflection and stresses. These methods have some limitations that are related with the complexity of the geometry, the loads applied, and also the behavior of the material. The finite element method is a powerful tool that uses numerical analysis and computational power to reach approximate solutions to complex problems that cannot be solved analytically, or its solution is very complicated to be developed. To apply this method in a two-dimensional shape, we have to split the structure or the body in a finite number of elements that are connected by nodes. This process is called discretization. When we apply the finite element method, the fundamental variable that we have to calculate is the displacement, because if we know how much the section displaced when the loads are applied, we consequently be able to calculate the stresses and the strength at the entire body. From this problem, we had a frame with two distributed loads. One load was 18,080 newtons per meter square, and the other load was 10,910 newtons per meter square. Then the depth was 4.48 meters, and the space between frames was 0.58.
I'm sorry. This is the depth of the draft. Mr. Ruiz, that's the draft, right? In this table.
Yes, Doctor.
Yeah, okay, go on.
General procedure, before we complete the discretization, then the stiffness matrix can be generated for each element, taking account the forces applied at the joints and the boundary conditions. With this information, it can be created a system of equation by the nodal force, the stiffness matrix, and the nodal displacement. It's important to emphasize that the stiffness matrix for this case will be for two-dimensional arbitrary oriented being element. Particularly, the stiffness matrix of each element can be assembled in a global matrix which defines how the entire structure will deform when the law is applied to it. Each local matrix has to be located based in how the elements are connected together, according with the continuity principle. Then a system of equations can be created. For this, it's necessary to define the geometrical boundary conditions and the nodal force. Now the displacement can be calculated using the big value method to decrease the complexity to solve the system of equation. When the deflections are obtained, it's possible to calculate the forces that interact with the body at each node. And finally, it's possible to develop an analysis of results to discern if the obtained values coincide with the nature of the problem.
Okay, next one. So in order to solve the problem, we once we have our frame, next one, we need to do the discretization process where we had next slide, where we have to establish some information. So here's a summarize all the forces, the distributed forces that we applied. The one is the one that is over the level of the sea. We know that is perpendicular. It have to be perpendicular of the surface, not just pointing like that, because we are going to have to find a correction. So for that, one of the hardest part is to calculate the contribution of the external distribution forces that are the ones that we show in the right part. And when we have that, we can do the corrections for each one. So we can have for every joint in the X and Y direction and the moment. So here is the formula that we use. We have to establish some conditions where we had the nodes that were going to be clamped and the ones that are going to be simply supported. So we can put it in the TXT that we are going to project. Next slide. We are going to use in the program, the TXT that we are going to use in the program. So here's a photo of the data that we implement in the program. We get a number of 21 elements because we try to use at least more than 9 elements in the bottom part, so we can get a similar as the shape that we have. And we have we try to make it general for every case, so that even when we have the Young modulus and the yield stress, it's constant. For this case, we tried to make it general, so we present the value if we have a different program with different elements. So we present the sectional modulus, the position of the nodes XY for the first one and the 2 for the second one, and we present where we have dx, dy, and phi. This is where we are going to have the conditions for when we have clamped or simply supported, or if we just don't know, we present a value of u for the unknown values, and fx, sy, and m theta is the values that we get from the calculation of the forces. And next slide. Next one.
To implement the program code, the first the unread file text file for extract the data, and after read the data in the for each element, and after create,
I'm sorry, who is talking right now? Is Ruiz?
Yes.
Okay,
yes.
go on.
Okay, after they create the matrix local for each element, and after they calculate the global displacement, which inverts the global matrix. Next. and create the matrix for each element, the T matrix for calculate the local displacement. And after the calculate the axial stress, shear force, and bending moment. And after the create the function for calculate a polynomial n1 and 2 and 3 and 4 for the deflection, and create the list of the lengths partition over the lengths over 10 for obtaining coordinates of the length for bending moment and deflection. And after the graph and the next, please. And after the graph and finally the describe in the text results.
Next one. Next one. As we can see, we try to resume. As you can see, we try to put most of the results together. This is the stresses and the moments that we get. We get a lot of information, even if the element do buckling or not. And this, because we had a lot of values, we try to focus. We try to see in the first graphic where we're gonna get our maximum moments, so we can focus on that. Because as you can see in the low part, we found the displacement and the force for the global and for the local elements. So if in the first graphic, we can see where we have the biggest moment, we can go directly to that element. So we can get the information from there. In the next slide, we do that. Next, please. So here's before. Here is a graphic that we implement in the program, so we can know if we are calculating the nodes correctly. Then in the right side, we have for every element. So because we know we're going to have the biggest moment in the element number 16, which is in the deck right in the last part, right? When we connect the side to the deck in that node, we're gonna have the biggest moment. That's why we analyze the deflection and the moment for that element. And then we graphic the deflection and the moment, as you can see in the low part. The one that we couldn't do because we have enough time was to implement the graphic in the program, So when the program see when we have the maximum values, just directly throw us the graphics of those elements. Next one. So as a conclusion, we found that this discretization progress was developed successfully because we solved the Python program. We proved it with a problem studied before, and we get correct results. So even though we couldn't implement, as we said before, the graphics, we think that this could be a good methodology to analyze bigger structures without having to do mathematically, like with a calculator. And yeah, that's it. Thank you.
Okay. Okay, a little bit long, okay, because it took about 13 minutes. But anyway, let's go to questions. Mr. Peralta, is here Mr. Peralta?
Yes, doctor, I'm here.
Okay, after solving the global equilibrium equations, okay, what's next step?
The next step to
No, I want to
when we
see in the code. Explain it in the code.
in the code.
Yes.
Code. Global. Where is the global? When we have the global equation, the next step is to create a list when we have the forces. When we have the global equation, we are able to obtain the values of the forces and the stresses. Then we have to...
No. My question is direct. Let's suppose that you solve for the displacements. Okay, what's next? And show it to me in, I don't know if you have a pointer or something, so I can see in the code, because yeah, okay, go on.
Here we have the global matrix.
Okay.
Yeah, the next step that we develop is to find the forces.
Okay.
To set the empty list to find the forces. We have to recorrer, I don't know how to say, the list L3, and we have to obtain the values of the forces.
Okay, that's the global, no, that's F dot append, right?
Yeah.
Okay, and then what's next?
The next step is we apply the big value method. Yeah, and we have to solve the global matrix.
Okay. Yeah. And then what? That's the next step. That's the one that I need to know.
Yeah, the next step is that we multiply first we have to calculate the global inverse of the matrix, and we have to multiply to obtain the deflection. Then we have the deflection, we multiply by the deflection by the original global matrix, and we have the external force.
Thank you. That's enough. Mr. Ruiz, this is a difficult question. How would you try to reduce the number of lines in your code, Mr. Ruiz?
For reduce number of lines, can create functions. For example, calculate the polynomials.
Okay. Makes sense. Thank you. That's enough. Ms. Vera.
Yes, doctor.
Explain me in the code, how did you calculate the stiffness matrix of an element? Of one element?
Yes, sorry. If we go to the first, here. No, yeah, that one. Wait me a second. For each element, first we have to establish the cosines and sines, and then we do this. We create our variables with KK1, KK2, and that's where we calculate. That's when
That's enough. Thank you.
Yeah.
Okay.
And we put it there.
Okay. Thank you very much. Isaac, let's go on with the next group.
Yep.
Thank you, doctor.
Okay.
Thank you.
Alarcón, Diaz, and Matias, are you there?
Yes,
Can
Dr.
you turn on your cameras, please? If possible. You can share the screen, so whenever you're ready, let me know.
Okay, Doctor. Can you see
Okay,
my
go. Yeah, I can see you. Go on.
Hi, hello everyone. This group is number 6, composed for to Yair Alarcón, José Díaz, and Oli Matias. The name of the project is Finding Element Methods Being Analyzed in the Outline. The agenda of today, it is composed for 4 parts. 1 is the introduction, 2nd, procedure, 3, results, 4, and conclusion and recommendations. For the introduction, the FEM allows us to analyze various types of naval structure or armors, however complex it may be. It helps to observe the individual behavior of the elements, deformation, shear force, and bending moment, with which it can be concluded that the structure may or may not be safe. The frame of the analyzed structure presents negligible deformations size. They are less than 1 millimeters. The normal stress developed on the elements that compose their frames does not represent a risk. However, the elements that compose of to the deck develop stress close to the yield point of that steel. The nation presented to the general objectives. The general objective of this project is to implement the finding element methods to analyze one of the plane frames of a steel ship structure using the Python programming language. For to the specific objectives, it's calculate to the equivalent load for each variable distributed force, calculate the displacements of each joint for each element, calculate the external force in each joint and the internal force for each element, calculate the axial force and stress force for each element, and check the convergence of the result using different numbers of elements. Next, my partner.
Next slide. The procedure. We will analyze the naval structure for 2 discretization. It will be analyzed for 16 and 9 elements. Now I will explain the process for 16 elements, which is the same process for the 9 elements. Next slide. We have the following file with the necessary information about the structure. The element file shows the joints at each element. It's necessary to obtain the length and angles. The joint file shows is the X and Y position of the joint. Next slide. And the property files with the Young modulus, area, and inertia of each element. Next slide. Now, then we need to obtain the equivalent concentrate load of the distributed force. For example, I have element 14 formed by joints 3 and 15. 15, and to obtain the equivalent concentrate load of the distributed force, we use the relation of the figure 3. Now, to obtain the concentrate load in the element below the draft, it is necessary to obtain the hydrostatic pressure distribution. As an example, we have element 2 formed by joint 2 and joint 3. We use the equation 1 to obtain the pressure 1 and pressure 2, and then to find the function that describes how the hydrostatic pressure varies in the element, we use the equation 2. And to find the external force acting on each joint, we use the integral of equation 3. Okay, next slide. Um, no. See. We have the external force acting on each joint for the global force vector. And then we obtain the Stephen matrix for each element. Next slide. Next slide. Yeah. To set the boundary condition, as we can see the figure 1, and in joints 10, 14, 17, and 1 are clamped. And then we identify the points where the displacement and rotation are 0, and on the main in the diagonal on the global matrix, we need to put a big value. And then we multiply this global matrix with the force vector to obtain the global displacement. And next slide. And then obtain the local displacement vector. It's necessary to multiply the global displacement vector of each element by the matrix. And to obtain the displacement local vector, we can find the deformation and the internal force and stress. My partner.
Good morning. I am going to talk about the result of this project. The global deformation that we found are less than 1 millimeter, except on the upper deck. The maximum deflation is 3 millimeters because we assume the joints are not central support. Also, in order to you can see this deformation, we use a scale to expand the displacement of each joint. We can see on the right node, the reactions prevent the node move. The blue color shows the initial condition before the deformation. The yellow color shows the deformation with 9 elements, and the orange color shows the deformation with 16 elements. After, next slide. After, we analyze the normal stress for each element with 9 elements and 16 elements. We can see for both graphs, the maximum normal stress is at the element 1 and 2 because these beams are supporting the pressure, hydrostatic pressure, and the pressure on the deck.
Just a second there. The units on the vertical axis are Newton per
millimeter
square. Okay. And these units are, I mean, the values are very small.
Yes.
Extremely small.
It's because the force applied on this beam are 200 newtons.
Okay, go on. I'm sorry. Go on with your presentation.
Yeah. Both graphs have similar values, but when use more elements, we can obtain a better approximation to real values because the convergence is fine. Next slide. So we can analyze each element and obtain the deformation at the local reference. In this example, we can see the analysis for the element number 2 that previously we showed you. This element corresponds to the frame under hydrostatic pressure. And is a strong element because the deformation is less than 1 millimeter. We can see the shear force and the bending moment are approximations because are linearly and constant function. This depends only, the shear force depends only the length of the beam or element. Thank you. Next slide.
Conclusions and recommendations. The precision of the results obtained by the finite element methods depends on the number of joints and elements, so that the greater number of these, there are more accurate results will be obtained. The analysis on each element will be more precise, for can be observed to the graph in the presentation. In this graph, where the formation curve for 16 elements has better convergence towards the solution than the of 9 elements. That is a presentation of the two results. This method is to analyze various types of naval structure or armors. For it helps to observe the individual behavior of the elements, deformation, shear force, and bending moment, and that is conclude to the structure may or may not be safe. For two recommendation, for future works, it's recommended that information that weights of the elements to be analyzed by provide has to influence the result obtains. It is also recommended to analyze the structure which the program uses to check the results obtained are correct. That is all. Thanks for the presentation. And next is to share to the code of the program.
Yes, show it to me, but let me ask a question on the code. So open the code so I can ask a couple of questions.
You see my screen?
Yeah, I can see the screen. Yeah.
That is the
Mr. Arcon, can you show me the code? Can you show me the code?
That is
okay. Okay, that's the code. For example, in what part of the code do you implement the restrictions? The restrictions.
The restriction is of using to file txt in this section to data to import that is obtained to the data for each txt.
It's in the part 2 when I form the matrix.
Property for two restrictions.
More down. Yes.
Condition for the method.
Yeah, but the problem is that in this case, you have to include every time you change the boundary conditions, you have to change this part of the code, right?
Yes.
Yes.
Okay. That's not very efficient way to do it. But anyway, yeah.
This boundary depends only the extremes that we.
Yeah, but the problem is that this implementation is not very efficient because every time you change boundary conditions, you have to change these lines.
Yes.
Okay. So Mr. Diaz. Let me ask something to Ms. Matias. Ms. Matias, in the results, can you show me the results? In the presentation, That's one. Okay, here, Ms. Matias, can you say about convergence comparing these results? Ms. Matias, can you hear me?
Yes, doctor. This can observe where the formation curve for 16 element has better compared the solution than the 9 element.
But you cannot say that one has better convergence because you don't know what's the exact solution. All what you can say is if you can, for example, let's take the first element, right, which has the largest stress. It's 6 point something. And if you use a partition with more elements on the left, you see that difference in stress is very small. So in one case, in the right case, probably I would read 6.2, right? In the left case, I would read 6.4. So the difference is small. So we can say that since the difference between these two partitions is small, we are very close to the precise solution. That's what we can say. Do you agree with me, Ms. Matias? No? See, what I'm saying here is that in your first partition, using 9 elements, right? In the element 1, you get an stress of 6.2, right? Are you with me?
Yeah.
On the left, what's the value for the stress in that element? What's the stress on the left figure?
Can you repeat the question, please? Doctor, I don't have what element do you speak?
See, on the left, you have the number of elements in the X scale, right? In the X axis. You say number of element. So I'm comparing element 1 on the left and element 1 on the right. And I can see that the difference of the stresses between these two elements is very small. That means that we are very close to convergence. That's what this graph is showing to me. That's all.
The element 1 and element 2 have the same value?
No, you have to compare element 1 on the right with element 1 on the left.
Yes, but the element 1 and element 2 on the left are the element 1 on the right.
Exactly. And the difference is between on the left and on the right is small. That means that you are close to convergence. That's the message from this figure. Okay, people, good work. Engineer Isaac, please let the next group come in.
Morning, doctor.
Good morning. Mr. Ramon, Mr. Lopez, Ms. Lopez, and Mr. Galarza.
Yes.
Whenever you're ready, you tell me so you can start. You can share the screen.
Okay. So can you see my PowerPoint?
Yeah, I can see the screen now. Who is speaking? Galarza. Okay, go on.
Yeah. All right. So my partner will start.
Okay. Go on. I like this figure. Go on.
Yeah. Good morning, Doctor. Talking about the frame of supply vessel apply final elements methods. The group is showmakers and members Virginia Monk, Giovanni Galarza, and Michelle Lopez. Next. Nevertheless, the first of striking of stop your from applying the game by Beirut. Agenda is the objectives, theoretical calculation, development program, analysis of results, and conclusion and recommendations. The objectives implement the final MS methods to analyze one of the plane frames of the steel ship structures and the characteristics of the vessel and the load for analysis. Next. Theoretical calculations. Since the ship is under hydrostatic pressure, the analysis focuses in the deflection of the beam elements. To simplify the calculate, we will analyze the beam's elements and the triangular trapezoidal lobes as its driving race. The equivalent force is obtained by replacing the distribution loss and the set describes lot. Obtain the constants for forces and moment and greater that below the draft. And therefore, the rectangular lot are the simplified to their geometry as point light of their knots, my partners.
All right, so for this case of the structure, we have done 3 discretization in order to check the convergence of the results. The first one is with 16 elements, the second one with 22, and the third one with 27. We did that because we want to approximate in a very good way the curvature of the ball. This is the main reason. All right, so now we are going to talk about a little bit about the program. We have to input the data. We are going to do the resolution of the matrix, and then we're going to analyze the stress and the safety factors. So for our program, we have to put the data in this way: the element, the node 1, the node 2, the angle, the length, the Young modulus, the area, the inertia XX, because we are going to analyze bending moment, and the inertia YY, because we are going to analyze the possibility of buckling when the elements are in compression. So we have done this data.txt file for the first discretization, and here we have to put the condition, the geometric condition, and the external loads. So we have 2 ways: when we know the displacement, like in a clamped end, and when we know the external force. So when we don't know one of those values, we have to put the letter UK. In order to the program, we'll recognize that, and then we'll find at the end. So these are the results that given by the program. For the first discretization, we can see that the stresses are lower. The higher one is around 71. And the normal and the...
I'm sorry. This is newtons per millimeter square or per meter square?
Newton per meter square.
Per meter square?
Yeah.
Okay, go on.
They were very, very low. So
very low.
For that reason, we have a security factor over than 2. As you can see, we have 7, 12, 13, and then. So I want to show you a little bit the program. It's right here. So in that part, the program will read the TXT file here, and then we'll divide in 2 lists, the mechanical properties and the condition. Then we find here the stiffness matrix for each one. And in this part, the program will we rearrange. I mean, with node 1, node 2, node 3, and all that. Then we locate the position where we don't know, when we know the force, I mean the geometrical conditions, and we replace by the big value. Then we solve for the displacement and then for the force. Then we proceed and calculate the normal stresses, and we proceed calculating here the security factor. So now my partner is going to continue.
Okay, to analyze the result obtained, we have divided of frame into 4 sections. Yes, main dig, side, and bulk. As can be seen in the graph, the value of displacement and normal stress tend to converge after increments to the number of elements in the discretization from the 16 element to 27 element. We also find that the maximum value of stress in the art above converts into pre-discretization. We have obtained the 69.48 Newton over meter square. On the maximum displacement value is a minus 0.33 millimeters. Okay. In this part, we will analyze the result of the stress and deformation. We will analyze by section to be able to better observation the conversion of the result in each element. Starting with the main deck, in which we observe in the first and second discretization have a similar stress because they only have a mid joint. Yes, but in the last discretization is was separate because at different distance, periodicity, the joint in the stiffeners. Of the displacement, we observe the converse of result because the distributed load is in negative vertical direction and the front of bucket. From the deck, in the stress and deformation, we have different graph because the number, the element of analyze is different. Is one element, two element, and four element respectively. Um, we observe the converse of result because it's same a mindic is a load distribution in negative vertical direction. Yeah. In the side, we have all the side. We can observe the displacement in the freeboard. We have a drawward deflection, and in the area of the draft, it is a deflection upward. As for the stress variation in the graph, is become a different joint considered for the analyze, having a very little dispersion of data. Finally, in the bulb, no, the last. Finally, in the bulb, the displacement graph convert and show an approximate of data. And the stress, you can check the greater number of elements, the greater approximation of you have. Next. In the present graph, the comparison of the displacement into whole on the frame. It's observed showing of the difference between the discretization.
Okay, finally, we can conclude that a discretization upper or forward than 27 elements is okay to analyze this structure, to analyze the stresses and the deformation. Also, we have checked that the maximum stress is located in the bulb, even though the maximum deflection happens in the deck. And we can conclude that it is because in the hull, we have the plate with more thickness in order to give more strength to the hull of the ship. So for that reason. And then as we can check, as we can see, the security factors are upper than do for all the elements. We can be certain that this structure will not fail for this load condition.
Recommendations. It's recommended to use many elements as possible to describe the section on this best way and choose obtain accurate results to analyze elements with curvature and verify the loss function of each element meets the corresponding pressure value on each knots. And finally, the recommendation to go through the structure in the same order to verify the convergence of the results by increase the number of elements in each discretization. Thanks.
Okay, right on time. A couple of questions just to check what you have done. Mr. Ramon, can you hear me?
Yes, doctor.
Okay, if instead of a frame, you would have a cable in your structure, okay, what would you change in your data? If instead, see, you have frames right now, or I have beams. Let's suppose one of them is not a beam. Now I change it to a cable. What data would you change to analyze this structure?
Oh,
What's the difference? Exactly. Go on. Say a little bit more. Exactly, go on. What would be the inertia in that case?
What inertia I change?
What value would you use for the inertia of the cable?
I increment the inertia.
No, the opposite. The cable doesn't have a bending stiffness, so the inertia should be zero.
Yeah. The inertia is over. Yeah.
Yes. Okay. Thanks. Ms. Lopez, in the computer program, okay, in what part of the computer program do you include the support conditions?
The conditions is in the big values, because in the file.
No, show me in the program, because I want to see if you know your code. That's what I'm trying to see.
In this.
what?
Can you read the data conditions, because
Okay.
the position of the forces and moments obtain equivalence, and the
No. My question is, once you're calculating, right? In what part of the program do you include the support conditions? The support conditions, the geometric boundary conditions. Where do you include them?
The boundary conditions in the big value.
Yeah, but show it to me. Show it to me.
No. Aquí está big value. No, no. Aquí está. No. ¿Dónde está Matrix? Ay, se me perdió. Ojalá. Podría subir. ¿Me puedes dar cuenta? ¿Podría subir? No, porque aquí no está. Ya, in this part.
Okay.
The displacement, the replace the boundary condition, obtain displacement because calculate the matrix inverse. More, está más arriba. Compañero, sube por favor. No, sube por favor.
No.
Arriba. Aquí está. Ajá. No, esto no es.
No.
No, entonces todo. Ay, ya me perdí. ¿Podrías? A ver.
Doctor, it will be better if Michelle shares screen, because she can move and
yeah.
For you. Let me Michelle share the code.
¿Dónde está Python? No me quiero decir Python. No encuentro mi. Aquí está. Dios. I see my screen.
Mm-hmm. I can see your screen.
In this part, matrix errors, condition, yeah. No, esto es calculamos la ecuación. Desplazamiento controlable que empieza. No, esto no es. Dios mío. In this part, the data of time replace the esto es la matriz y aquí viene la posición de los desplazamientos.
No, I don't have the time. Mr. Galarza, would you explain it to me?
Yeah, of course, doctor. Let me share the screen because. All right. So as I say in the first part, we put TXT file, right? So in that part, we put. Let me share. Right here. So in this part, we put the condition, the external boundary condition.
Yeah.
And you say the support. All right. So we have that in the text file. So
Okay.
when the program read that, it will store that values in the matrix conditions. So then we proceed and then we find that right here. In this part, the code will recognize where is the
Thank you,
unknown
thank you,
forces.
thank you, thank you. That's enough. Okay, Engineer Isaac, please, would you please let the group, the last group come in?
That's it, doctor. Thank you.
You're welcome.
Thank you, doctor.
You're welcome. Will you please turn on your cameras? Okay, whenever you're ready, let me know. You can share the screen.
Can you see our screen?
Yeah, I can see your screen. Go on.
Good morning, doctor. My group is confirmed for Jan Leon, Liliana Vega, and Alex Valle. The agenda for today is introduction, discretization process, programming, result, and conclusions. The object continuous systems and discretization system is equal discretizations, elements and nodes.
Nice.
Defined elements methods FEM is the method for solving problems of engineering and mathematical models. It is based on matrix algebra to solve system of simultaneous equations. It is also called as matrix method of structural analysis. In our discretization, we select 15 elements and 50 joins without consider the elements on the kill line because we consider it as a strong element. Also, we start this process by calculation the longitudinal of the elements and the effective inertias using the Schat curves for distribution loads for calculate the effective breadths. With the material properties, we construct the element matrix. Also to obtain the global matrix, the matrices of each element are combined. According to the joint connections, the inverse is multiplied by the external forces and moments to obtain the global displacement in the each joint. We need to convert our global displacement in order to get the axial forces and stress. And finally, using the polynomial equations, we can determine the shear force, bending moment, and displacement for every element, and then calculate the normal stress due to bending as well. Continue.
Vessels in general are exposed to punctual force, loads, and the hydrostatic pressure. For this, we need to analyze what happened with the structure elements. In this case, we are analyze the frame, are exposed the different geometric loads, like triangular loads, rectangular loads, and the combination of the both. As a finite element required the vector equivalent force and moment for determining the vector displacement. We are simplified the force, the punctual force in the joints. For this, we are used to the equation for this type of the geometry loads. Next. there is the flow chart. The more important in the flow chart is start, open the file, read the lines. Next, split the elements with the characteristic com. And next, this program calculate the length and angle from the coordinates, then the joints. And next, generate the stiffness matrix, then generate the global matrix. This program completes condition for the boundary condition, and then obtain the inverse matrix for the obtain the vector displacement, and continue complete the condition for the terminal stresses, and finally write the result and the fine. And
you're muted. Everybody's muted, please. We're not listening.
Okay, so sorry. Okay.
Go on.
About the programming, I will not show in detail because it's a large process, but I will highlight briefly some part of the code that I consider are important. The information or the enough information that the computer program needs to read according to the requirements is the number of elements, the number of the initial and final joints, the coordinates, and the material properties for the first part. And the second part, the boundary conditions and external force acting in each joint. As we can see in the top left box, it shows how we calculate the angle for the local reference system. Firstly, we have to identify if we deal with inclined bars or vertical or horizontal bars. And how we do this? By subtracting the joints, the positions. If it's negative or it's positive, so we can define in what direction it's working that bar or that beam. And so we can state the relation for the angles. In the right hand side, in order to assemble our global stiffness matrix, first we have to enter with a first value of a row and a column into a loop, and simultaneously running the whole matrix in the X and Y direction by skipping three positions, 3 steps. First, to the top left and top right, down left and down right. Then we know that the stiffness relates that the displacement and diagonal joints and apply force in diagonal joints. So we need the program. We need to read that information. In the box low down, we can see that I put a condition in the vector of displacement in the global. If the program identify a letter X as a string, if that value is different than X means that it's unknown. If the program identify X different, so that is a value of 0 or other value, get the position in the vector, and that position it will be the same, and the X and the Y direction in the big K matrix. So I place it in the diagonal direction, and I put a big value, and so on. Okay, are the input and output data that I mentioned before. These are results, but the table that is of interesting is the table low down, because the program for each element calculates the bending moment at along of the element of the span of the element. But here in the table, I put it just the x0 and xl, because it's commonly that we found the maximum and this point. Yeah, and then I select the maximum. The program select the maximum bending moment, and we analyze what's happening at the top and the bottom. Yeah. And the total stress, we show that because we have to add in the actual stress as well, the summation of that. But okay, let's analyze our results in a more practical way. The graph in the right is a graph that our program also provide us. Let's analyze what happens in the element 5. The program say that the maximum bending moment is in the x equal to L, but according to our discretization, our element 15 run from the right to the left. So the x equal to L is located at the strong element on the key line. And we at first stage we have to find that element is a solid foundation, so provides the elements almost perfect clamped condition. And we can see in the graph that there is no rotation, there is no displacement, and a negative bending moment is acting on that point. And what happened at the other side in the connection between deck and the site, there is no displacement, but there is a final slope. It's proper to the simple supported. Finally, to finish this, what's happening in the element 14? There is a positive bending moment, and the fibers and the top are in contraction, so it makes sense according to the graph are consistent. And other thing that in that part of the beam, we have to take care because it's absorbing a lot of energy, so it's a large deformation, could be failed because ductile modes of failure as well.
The code give us the total value of the force and moment acting in every joints, in which the force and moments calculated in an analytical way must be subtract to obtain the reacting and external moments at the clamped elements. How see in the element 1, the force product of the pressure have two components because we obtained the two reactions in x-axis and y-axis.
Try to complete the conclusions because we are, okay, go on.
And the conclusion, the program estimate a stress distribution, displacement, and the graphic displacement over a complex geometric system using the finite element method in the plane. This work concludes with the coherent summary of the behavior and response of the structure. In addition, a converged analysis on the result can be easily obtained by modifying the data input required by the develop the software. Thank you.
Okay, Ms. Vega, in the code, can you show the code and explain me how do you the full code? Don't you show? Can you show me the full code No, the total code. Can you open and show and stop sharing this screen and try to show me the full code, please, if possible.
Doctor, I compare the total cost.
Yeah. What is the total code? The code. I want to see the computer code because I want to ask some questions about it. Okay. Okay, now we're cooking. Miss Vega, how can you explain to me the process to form the big K matrix?
The big K matrix.
Yes.
The first generate the matrix. For this, consider 3n for 3n, where n is number of the element, number of the joints. Then the first I create the stiffness matrix. The stiffness matrix is
What, can you show me where this stiffness matrix is generated?
Sorry.
Can you show me? You're saying me that before
the stiffness matrix.
Yeah, just a second. Listen to me. You just said to me that before forming the global stiffness matrix, you are to form the element stiffness matrix, right? I'm asking you, where can you show me where do you form this matrix? Go on.
How assign the element for global matrix.
Exactly.
Use the 3 multiplied by n minus 1 for assigning the element.
That's enough. Thank you. See, all what I need is to check that everybody was able to work on the product. Mr. Valles, okay. Do you explain to me in the program, how did you calculate the axial force, the axial internal force, P? How did you calculate that?
Thank you, Doctor.
How did you calculate that?
Yeah. This force is calculated for the obtain the inertia of the each element and area of the each element, but all the elements that load axial. This load is in the in the joint 15.
No, but this is no. The general case, you have to calculate for every element. You have to calculate the axial force, not for one single element. You have to calculate that for all elements.
The matrix local.
No.
In the local display.
The question is exactly. Go on.
In the local displacements. Is multiplied by the stress?
No. The local displacement, you don't multiply that by the stress. I want to calculate the axial force.
For Young modulus.
See, you have it there, but the problem is that you're telling me that you did not work on this part. That's what worries me. So I need to be certain that everybody understands the process. My question is clear. how did you calculate in your computer program the axial internal force P, large P, capital P?
In general, the global matrix, excuse me, the external force for the displacement local multiplied for forces for internal forces.
Mr. Leon, could you explain that to me? How do you calculate the internal force P, Mr. Leon?
Yeah. ¿Dónde está? No. Yeah. Okay. Firstly, we have to before we have to we have calculate the global vector displacement. Then we multiply this vector by the transpose matrix.
Transpose, yes.
Transpose matrix, and we obtain the local displacement. And then we calculate the stress. The stress, as you see in the line 159, we
Thank you. Thank you. That's enough. That's enough. Thank you. Okay, people. Nice work. Nice work. The problem with your report is that I don't see any convergence study. I just see one single model, right? How can you be certain that your results are adequate? Remember, you always have to do a convergence analysis in order to be sure that your results are close to the correct one, because we do not know the analytical, the precise results. So we always have to be worried about how close we are our result from that precise, exact analytical result. Did you calculate any other results for other partitions?
Yeah, we did it last night. Other discretization, but we decide in group that we don't show that results because with two values it's difficult to make an analysis convergence. But the results that we obtained was a decreasing of the stress in the joints that.
Yeah, but remember, I am an engineer. When you say decreasing, how much is decreasing?
Yeah, it was 10%.
So that means that you're close to convergence. Mm-hmm. What I would suggest is that why don't you write an appendix and send it and try to load it as soon as today, because it's always very important to include that. Okay? Okay. If you have the time. Okay, people, thank you. Bye-bye now.
Thank you.
You're welcome.
Thank you.
Oh. ¿Cómo estuvo?
Bien, doctor.
Qué locura. ¿Cómo están los niños?
Aquí tengo uno llorando.
Hay una tremenda diferencia de 1 a 2.
Sí.
¿Cómo estuvieron las presentaciones? Realmente hay algunos grupos que están muy bien. Pero hay
Muy
otro-
bien de inglés, claro. Como dos grupos creo que están bastante difíciles.
Ahora, cuando ustedes revisen el proyecto, una de las cosas que quisiera. No, tranquilo, solo un minuto, solo un minuto. Me gustaría que revisen en detalle, pídale esto que lo haga a Génesis. En detalle que vea los códigos y trate de detectar si alguien ha intercambiado pedazos de código o lo que sea. Inmediatamente, eso es su trabajo. Yo les voy a pasar ¿cómo se llama? No, bueno, yo lo que voy a hacer es lo siguiente. Yo les voy a pasar un poco más preciso los detalles de qué considerar en la rúbrica. Y, por ejemplo, cuando se analiza resultados, ¿qué cosas hay que considerar? Convergencia, ta. La otra cosa que me preocupó mucho es que, por ejemplo, algunas personas dicen los esfuerzos son, qué sé yo, 300, 400 newton milímetro cuadrado. Y eso no se espera. Si usted siguió las reglas, es difícil. Hay un factor de seguridad tras otro factor de seguridad y va a ser difícil. Entonces, esos resultados hay que ponerles especial atención y hay que penalizar el hecho de que los resultados no están correctos. Porque no es solo cuestión de obtener números, es cuestión de obtener números y pensar que si eso tiene sentido o no. Listo, entonces una vez que haga eso, yo le paso, como dice, un detalle de qué considerar para evaluar los reportes y ni hablar. Va a tener que hacerlo usted porque yo estoy súper ocupado. El día viernes, ¿el examen a qué hora es? A las 8.
No sé si usted especificó en el sitio web.
Ya, no, ahorita lo voy a revisar. No, es que tiene que ser de acuerdo con lo que está especificado
Perdón.
Ok, entonces, porque eso me está preguntando Rubén. Usted ya tiene los exámenes, ¿no es cierto?
Sí.
Entonces, ni hablar. Ahorita yo confirmo la hora, le digo a él y los dos se ponen de acuerdo para estar temprano. En ese momento yo voy a tratar encendido el celular por si acaso alguna pregunta. Pero yo resolví en detalle el examen, usted lo ha resuelto en el examen,
no hay problema.
Están correctos, están claras las figuras, no debe haber ninguna pregunta.
Sí, todos los datos están ahí. Sí.
Exactamente. Por favor, me pasa sus comentarios de esta presentación para yo hacer un solo compacto.
Ya, ok.
Gracias.
Hasta luego.
Hasta luego.
Okay.